Hello, good morning everyone, and let's get started. Just give me 1 minute. I'll enable a chat box. Okay, so far we discussed, in last class we discussed the details of assignment. Prior to that, we discussed the Strassen multiplication algorithm. And today is the last topic. We look at divide and conquer algorithm, the or decrease and conquer algorithm. What are the advantages, disadvantages, and from next class onwards, that is next week, we'll start moving to greedy algorithm. If my audio is not clear, let me know, put in a chat box. Otherwise, I'll continue. So mostly this is from the book of Levitin. You can look at. So let's look at divide and conquer and what are our advantages. If we look at when we do a problem divide and conquer, essentially what we are doing, we are reducing a bigger problem to a smaller problem. And because it is a smaller problem, we are able to solve the smaller problem and then build upon the smaller solution to build up. So rather than solving a bigger problem, solving a smaller problem much easier, and that's the benefit or the advantage the divide and conquer approach gives us. Further, when you do divide and conquer, because we are dealing with a small problem, it becomes more efficient rather than solving whole thing together. And so rather than doing a brute force approach of solving whole thing together, we are trying to solve a smaller problem that becomes efficient. And that's another benefit divide and conquer approach gives us. And we have seen that, let's look at a binary search. When we do binary search, rather than searching for an element in the entire array, we divide the array into half, we divide it further into half, we keep narrowing down the scope, and finally, when the array size becomes 1, we are able to eliminate. And that's the benefit the binary search gives. Day before yesterday, we also looked at large number multiplication using Karat-Sobel algorithm. Using Karat-Sobel algorithm, we again divide number into two parts, further in two parts, till we get into one digit number each, and then we are able to solve that as well. So this is what we basically get. Same way, we also look at Stockton's matrix multiplication, where we split n by n matrix into n by 2 into n by 2, and the benefit we got is rather than doing 8 multiplications, we end up doing 7 multiplications, and that's why we get more efficiency approach. So essentially, our order of time complexity reduces, and that's the advantage our divide and conquer approach gives us. We have seen the same thing in merge sort and quick sort. We basically keep in merge sort, we divide the problem into two halves, keep dividing it further, till it becomes size of 1, and then merge it. Rather than sorting whole thing, we are assume one element is sorted and merge it. The same is true in quick sort. We partition differently in such a way that we do in place merge, and we don't need extra memory as required in merge sort, and that's a benefit. Further, if you have a parallel systems, like most of the time a multi-core systems or multi-core processors, so if you have a large number of small problems, we can solve them in parallel. Let's say we do merge sort or the quick sort. If we do two partitions, these two partitions could be solved separately. The two partitions become 4. If you have 4 CPUs, we can solve each of the 4 partition problems on a separate of the CPU, and hence smaller problem can be solved in parallel. And because this can be solved in parallel, our total computation time or total solution time. May I request those who are probably keep your mic in the silent mode so that others can hear. Thank you. And we also, it's a smaller problem because a smaller problem can easily come in system cache. Cache is always a small size, and because it easily comes in system cache, and solving a problem in system cache, it solves it easily. We are efficient, and we are probably better off. I request you guys to keep your mic off. Further, so let's look at these are the advantages to look at, but certainly everything comes at a cost. And let's look at what are the disadvantages of divide and conquer. If we look at primarily whenever we solve the reconciliation, whole divide and conquer or decrease and conquer depends heavily on recursion. We depend upon recursion, and recursion means we keep making function calls again and again. Everything goes on to stack, and that way our computation become little bit slower. Further, because of recursion, we need more memory because we have to pass all the parameters onto the stack. So it requires a little bit more memory than if you've gone through the iteration. These are still minor problem because today's system we have enough memory and probably systems are faster. But the major challenge with recursion is implementation of recursion. Implementation of recursion requires complete clarity because you always have a terminating condition, and if we make a simple mistake of terminating condition, it can go forever and never terminate, and this becomes a real challenge there. So when you implement recursion, one has to be very, very clear how the problem is to solve, what is the smaller size problem, what are the conditions where rather than calling a smaller problem, I need to return right there. And that clarity is, if you don't have, you'll probably make a bigger problem in that sense. The using recursion requires little more clarity. Iteration would have been simple enough, but recursion could be a little more complicated. So, and that's the reason it's a bit complex, and that's a disadvantage we can look at. For example, if we look at print all digit decimal numbers, if I need to print 1 to n, I count iteration and say print 1 to n, and I'll be print a simple problem. But if I were to do recursion, I say first print all the numbers of 1 digit, then I've done 1 digit, then solve a problem of 2 digit, solve a problem 3 digit. So it requires a little more complexity. In that sense, programming becomes a little tougher when we use recursion. Any error, even a minor error in recursion termination conditions, will create a problem at the right result. It may go an infinite loop. It may not give you advantages there as well. And sometimes we think it's better. So let me just take a simple example of power computation, and I'll tell you what do I mean by it's really giving advantages there. Let's look. When we do power n, we say if n is even, most of it did say return power n by 2 star power n by 2. If we are doing this, we are actually not making any benefit. Why? Because we are solving power n by 2. We are again invoking power n by 2. And that means our original problem, the time complexity Tn becomes Tn by 2 plus Tn by 2, which is 2Tn by 2, and which basically gives me order n. So recursion is complicated. We use waste more memory in a stack. We're not saving any time in computation. So what should be done? What needs to be done is, rather than invoking power n by 2, again 2 times, what we should do is compute power n by 2 once. Say x is equal to power n by 2 and then return x star x. Now we are doing one multiplication, but the recursion we are calling only once. We are calling recursion only once, whereas in this case, power n by 2, we are calling recursion twice. If you say power n by 2 star power n by 2, we are not getting any benefit because we are calling twice. But if you do compute once and then use x star x, we are calling recursion once, and because of this reason, our time complexity becomes order log n, whereas in the case of calling recursion twice, my time complexity becomes order n. So one should be very clear about how when to use recursion, how to do that, and unless that clarity is there, programming may become complex, and that's the reason we said that is the disadvantage with recursion. The next one, let's look at, since we are dealing with continuous stack, and if we have too much stack invocations, normally a system has a limit, maybe 8,000 calls or 10,000 calls, whatever, and our recursion goes that much deeper, we will run out of system memory and program will not be solved. So we have to make sure that when doing recursion, we should never exceed the system configuration parameter and run out of memory. There's other part we have to look at. So further, other thing is we said the if subproblem repeats, like in Fibonacci series, subproblem repeats, are we solving the same problem again and again? If we're solving subproblem again and again we're wasting CPU time, and that is where we come into dynamic programming, where we solve one subproblem only once, we don't solve it again. We store the subproblem, like in power n by 2, we store the results and reusing it. If you don't do that, we are wasting our compute time, and then divide and conquer doesn't give any advantage, and there is another disadvantage of divide and conquer. So let's look at the another variation of divide and conquer. Typically, divide and conquer, we divide one problem to multiple problems, 1, 2, 3. But there's something variation called decrease and conquer. In decrease and conquer approach, we basically solve only one problem at a time. We never divide the problem, we reduce the problem size. So whatever problem size n is, we reduce to n minus 1 or n minus 2 or by some factor, but we don't split problem into two. We're reducing the problem size by 1 and then solve that smaller problem and continue with that. And using the smaller problem, we use that smaller solution to build upon the larger problem, and that is what we basically do. Now in the approaches of decrease and conquer, the approaches could be either we could do top down, which is recursion, or bottom up solve, and then keep building upon it, or those kind of choices there. So let's look at the differences between divide and conquer versus decrease and conquer. In divide and conquer, a given problem is always divided into smaller parts, and we always solve all the smaller problems. In divide and conquer, a problem could be divided into 2 parts, 3 parts, 4 parts. Like in a Strassen matrix multiplication, we divided into 4 problems. A1 matrix A1 got divided into A1 and A2, A3, A4, divided into 4 parts. If you do, let's say, quick sort, we divide it into 2 parts, and we need to solve all the smaller instances. And that is what is called is conquer approach. And then we merge the smaller instances, and based on how do we merge, we basically write a recurrence relation. So in this case, solving a problem of size Tn, we are basically solving a number of problems, each of size n by b, and this is my cost of conquer, and that is what we basically do. In decrease and conquer, we reduce the problem size by a certain amount. It is not that we make into half or something by few numbers or by few little factor, and any point in time we always have only one smaller instance problem we never have multiple small instance problem, and that way the decrease and conquer becomes comparatively easier to implement. And we use the same approach to solve it. So recurrence relation for decrease and conquer becomes Tn is equal to a smaller size problem Tm, where m is less than n, and then we have the conquer part of it joining from using, when you solve the problem of Tm, how do we use this solution to build upon Tn, and that's the work called F1, and that is what we say is the conquer amount of work. So let's look how many different kind of decrease and conquer approach can be there. First is we decrease by a constant size. It's typically by 1. For example, when we look at decrease and conquer, let's look at sum of n numbers. We can find sum of n minus 1 numbers. We're decreasing by size 1. Or let's say look at the reverse. When I'm solving reverse a string, so if I'm solving a reversing a string, let's say my string was A, B, C, D, E, F, G, H, I. So I know that reversal I can decrease by 2 and solve the, so this is a string of size 9. If I can solve a string of size 7, if I can solve a string of size 7 B to G, once this is solved, I can swap I and A here, and whatever the solve with the 7, I can solve with the size of 5, which is C to G, and then I can solve H and B, and that way. So in this case of reverse, implementing a reverse of a string, we are reducing by 2. In the case of sum of n numbers, we are decreasing by 1. So depending on what the problem is, and you look at our one question did in assignment, where I'm saying the section A student, section B, and we need to make it AB something. So again, we are decreasing of size by 4. So C is the number, so typically it is 1, but could vary 1, 2, 4, or whatever size you want to divide. It need not be constant always, sometimes it could be varying. I'll come to the sort by. We look at the example, insertion sort, we decrease by 1. Graph traversal, we always take one node at a time, so we decrease one at a time, we decrease size by 1. Topological sort, once we discuss, we'll again see we decrease by 1 graph problem. So typically any graph traversal, we decrease by 1, or this is what we basically do. Other is to decrease by a constant factor, and that means what a number is, take some 1% off, 2% off, or even half. Like when you do binary search, a given problem, some elements A, B, C, D, E, something, we divide into half, discard one half, my C becomes 2, my size becomes n minus n by 2. This is what typically happens. So we reduce by a factor of a problem, or if I'm doing 3 parts, I can remove n by 3 part and then solve. So decreasing by a constant factor, like what we did when I solved the Hanoi tower with 5 towers, we decrease by a factor of 3 and solve that way. So we look at that part. Similarly, like binary search decrease by half, that could be the other way, and we looked at that. Binary search, exponential by squaring again, x is equal to power n by 2, and we looked at those problems. Other is we decrease by a variable size. Sometimes we decrease by 1, sometimes we decrease by 2. I think for one section, I played a game like NIM-like game, where depending on, and the NIM-like game is something, assuming I have given you a number of cards on a stack, let's say something, so I have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I give you 12 cards, and this is, I'm talking about a game called NIM-like game or NIM game. This is described in Levitin. I also played this game on the last day of class in section B, I believe. And essentially game is, I ask you to remove any number of cards from this up to maximum up to 3 or 4. So when I ask you to, let's say, remove any number of cards up to 4, now if you remove one card, then I will remove 4 cards. If you remove 2 cards, I'll remove 3 cards, and so on and so forth. And we can basically look at the person who plays first, or the person who remove at the end, he is the one who is going to win. And that is what we are basically trying to look at. And that essentially what I'm trying to say. So this is name like game. So sometimes I decrease the problem by 1, decrease the problem by 4, decrease the problem by 3, and that is what I mean by decreasing by a variable size and not always a fixed size. Let's look at another case. We all know finding greatest common divisor GCD, which is GCD of Mn is GCD of M mod n. So initially, let's say my problem was, let's look at, I need to find GCD of, let's say, I would say 40 colon, let's say 24. Now this will basically involve, next invocation call would be GCD of 24 colon 16. So I reduced not by a 40 became 24, 24 became 16. I decrease problem by 16 and problem by 8. So essentially I'm decreasing by 8. Next time I do decrease by 8, next time by 4. So decreasing a problem by a variable size and not a fixed size. So that also happens. That's the meaning of decreasing by a variable size. And basic problem is this. So look at, when you do decrease, it need not be a constant factor decrease. It could be a variable number. That's what we look at. So how many, we already did that. A name player like game says a pile of n disk. Each player picks up minimum 1 and maximum m disk. You can actually make a pair of 2, play this game at your home. And if you play this game, you pick 1. And if you know the total number of disks is a sum factor of k into m plus 1, then if total number of disks are k into m plus 1, where k is any positive integer, then the person who plays first, he ends up losing it. So let me play how does the game work. Let me draw 12 disks. So I say 12 disks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and let's say this is 12. And I'm saying, let's say m is equal to 3. So I'm asking you to pick up either minimum 1 or maximum 3 disks. And since m plus 1 is 4 and 12 is a multiple of 4, that means the person who plays first is going to lose. How? Let's say you are the first person, you pick 2 disks, throws away. I'm second player, I know the number 4, m plus 1, I subtract 2 from 4, I'll remove 2 disks and throw them away. So we'll look at this point in time, we still have 8 disks, and 8 is still a multiple of m plus 1, which is 4. Now if you pick 3 disks, let's say you as a user pick 3 disks, now I'll pick only 1. And again we are left with 4 disks, which is basically, now if you pick only 1 disk, yellow you, if you pick 1 disk, I end up picking 3 disks, and because I emptied the stack, I am the winner. So name game like if you have n disks and n is a factor of m plus 1, then the person who plays first is going to lose, and person who is going to play at the end is going to win. So this, again, we are decreasing problem by variable size, and then what basically game is. I suggest to play game at home, and you probably know how the game will look like. Now we can look at difference problem with the depending on how the different approaches work. Let's look at a simple case. Let's say we need to compute x raised to power n. In decrease and conquer approach, we'll compute x raised to power n minus 1. So if we can find the solution of x raised to minus n minus 1 and then multiply by x, we should do that. So let's say I have a function, I need to compute x raised to power n. So I would say fn, because n is the variable, x I know. So if I can solve fn minus 1 multiply by x, I'll get x raised to power n. This is decrease and conquer by 1. Other approach would be brute force, multiply x by itself n times, which is basically for loop. So write a for loop, answer is equal to 1 for I in 1 to n, answer is equal to answer is star x. This is a brute force approach, and A would basically give me the power of x raised to power n. So this is a brute force approach. Next approach could be, we look at divide and conquer, as you said, power of n, divide by 2, x raised to n by 2, if n is even, and if n is odd, we divide x raised to n minus 1 by 2 multiply by x raised to n minus 1 by 2 into x. So again, with this divide and conquer approach, we decrease the problem size to half and solve it, and this is what basically we do in our case. Other approach is by a constant factor. I can say n by k and multiply x raised to n by k. That when you take k times, we will again get the answer. My recurrence lesson would be this, and again, you basically get order log n solution. So let's look at a beautiful example of how to use divide and conquer or decrease and conquer approach. So again, this example is given in your Leviton book. So celebrity problem is, let's define a celebrity. Just question 10. A celebrity is a person in a group. A person is such that everybody knows that person, but that person does not know anybody. For example, we can say in our class, there's a person or there's a new teacher, Kevin. The new teacher doesn't know any of the students, but all the students knows the teacher, or in that sense, you become a celebrity. Or in the class, all of you know who the principal is, but principal does not know any of you, so principal would be celebrity. So in a group, the problem is, in the given a group of people, can we find, is there a celebrity in this group or not? So, and to find a celebrity, the question is, you need to ask questions, people, do you know him or her? And that's the way only we can find out. So each one asks, you ask about other person, do you know him or her? Answer is yes or no. And based on that, you can decide whether it's a celebrity or not. So the question is, we need to design an efficient algorithm to find the celebrity by asking this type of question, and how do we approach this problem? And let's look at what the different solutions are. And our efficiency of algorithm would depend upon how many questions we're going to ask. The less number of questions we ask, better the algorithm is. More number of questions we ask, worse our algorithm is. So let's look at simple brute force way and then see how does our decrease and conquer problem makes it simpler and easy to solve. At least we need to know about each person. So minimum time we need is order n, but let's see how can we get order n, but starting from base case. Let's say we look at adjacency matrix. So adjacency matrix is like this. This is I and j, and this entry of I and column j is 1. If I know j, if I knows j, then aij is equal to 1. If I does not know j, then aij is equal to 0. So the adjacency matrix has only 2 entries. If this is value is 1, that means I know j, otherwise value 0. Now using this, can we figure out the celebrity? So all we need to do is, let's look at this matrix. And in this matrix, number of entries are n square, because we're going to ask each person, do you know other person? Except the diagonal part of it, we'll assume that will not count, knowing by himself, because everybody knows itself, so that is not counted. So we are looking at all the entry aij for I1 to n, j1 to n, asking everybody that question, and that means we are asking n square questions. And how to find the solution? We can look at a column. If this column has all the entries as 1 except the diagonal entry, so that means total number of sum, if I sum this column, if the value happens to be n minus 1, so in this celebrity case, in the brute force case, let's say look at the column. If all column except the own, let's say X was celebrity except that himself, if every other entry is 1, that means sum of the column entries n minus 1. This implies that person 1 knows, let's say this person is K, person 1 knows K, person 2 knows K, person 3 knows K, person n knows K. So that means K is a celebrity, and further the row corresponding to K, the row corresponding to K, this row should be 0 because this celebrity should not know anybody. So if the sum of the column is equal to n minus 1 and sum of the rows for the kth element is 0, we know K is celebrity because K does not know anybody, but everybody knows K. And in this, we have asked n square question and we could find the celebrity. But this takes n square question, which is highly inefficient. Let's look at, can we do better than this? Other is we can use what is called adjacency list approach. Adjacency list means basically build a graph. So node I, draw a edge to node J only if I know J. If J knows K, make a directed graph I to J, I know J. If J knows I also, then you put reverse edge, J knows I. So basically, if node I person I knows person J, draw the directed graph edge. And when we build such a graph, now how do you know what celebrity is? So if we have a node, some node K, who's in degree, that means who has an edge from each of the node 1, 2, 3, K minus 1, K plus 1, and so if I have a n minus 1 number of incoming edges and my outgoing edges is 0. I have no outgoing edge, but I have all the n minus 1 incoming edge. That means n minus 1 people knows me. Person K does not know anybody. In that sense, K becomes celebrity. Using adjacency matrix, we say if adjacency matrix sum of the column is n minus 1, and for the sum of the column K is n minus 1, and for the kth row, if sum of the row is 0, then K is celebrity. In adjacency list case, we build a directed graph. If for any node K, if in degree is n minus 1 and out degree is 0, that means the person is celebrity. But how many questions we ask? We basically, again, total number of questions we ask is n square, because we draw edge, we don't draw edge, but we still need to ask a question. So this is what we do basically. This is the number of edges, we know that get problem. Third is, can you do decrease and conquer? Essentially, let's define a function celebrity n and which returns k. And that means if k is equal to n or k is a non-zero, that means k is celebrity. If it returns k is equal to 0, that means there is no celebrity exists. So how does this approach would work? We call this function celebrity n minus 1. Celebrity n would call celebrity n minus 1. And let's say celebrity n minus 1 returns k. Celebrity n returns k. In this case, that means among the n minus 1 people, k is a celebrity. But for real celebrity, the nth person also must know this kth person, and this k should not know another person. So we still need to ask two questions. So, and that means we're doing order one work. So if celebrity n minus 1 returns k and k is non-zero and another person knows k and k does not know n, then we can say k is celebrity other. Or if the k is equal to n, the last person, that means all the n minus 1 people knows n and another person does not know and becomes celebrity. And so complexity is, because we are solving a problem, in that case Tn is equal to celebrity Tn minus 1 plus 1, and we get the answer. And that is how the celebrity would work. If k is not equal to 1 and knows k is a celebrity complex 1, we looked at that. So in either case, we are able to find celebrity in order n time. Could there be another approach? This little complex using stack, we can still do that. And so look at what is happening here. Sorry. Come to decrease and conquer. So look what we're trying to do. If k is equal to n, let's say celebrity returns n value, that means n minus 1 people knows nth person, but we need to make sure the nth person does not know anybody. When nth person does not know anybody, we need to ask n questions. So my time complexity would be Tn would be Tn minus 1 for returning this and checking whether nth person knows everybody or no. Because if another person knows anybody, then it's not a celebrity. If another person does not know anybody, so we need to do order n work here, because we need to check with if k is equal to, so celebrity n minus 1 returns k and k is equal to n, so this work is t of n minus 1. This work, so Tn is Tn minus 1. So when k returns n, that means all the n minus 1 people knows n, but another person we need to ask each one, do you know first person 1, do you know person 2, do you know person n minus 1. So we need to do order n work, and if we solve this reconciliation, this will basically give me order n square. However, if, so sorry, I think there is a error there, so this complexity should be n square. But if k is not equal to n and k is not 0, that is among themselves they are celebrity, all we need to know is ask k, do you know n, and ask n, do you know k, only order 1, and in this case my recurrence relation happens to be the order 1. So in this case my recurrence relation would be Tn is equal to Tn minus 1 plus order 1, which will basically give me order n. In this case, checking whether nth knows everybody or not requires order n work. So one equation is, but in this case my equation is Tn is equal to Tn minus 1 plus order n, and when k is not equal to n, my recurrence relation is this. And since this is a higher term, we solve it. Solving this equation will give me Tn is equal to order n square. So even doing decrease and conquer, it still gives me n square time. Whether you would adjacency matrix, adjacency list, or decrease and conquer, I still got order n square. Can we still do better? Look at problem differently by decrease and conquer. And the next approach is what we call is using a stack. So let's say using a stack, put everybody on the stack, and I put everybody on the stack, my stack size is 1. And my objective is decrease and conquer means keep reducing stack size by 1 at a time. So how do we do that? Keep repeating till my stack size becomes 1. So I'm decreasing my stack size by 1 at a time. The way work is, take 2 people off top 2 from the stack, A and B, and if A knows B, that means the A is not a celebrity, because A knows B, and the definite celebrity is the celebrity should not know anybody. So if A knows B, that means A is not celebrity, because celebrity is not supposed to be knowing anybody. So he is not celebrity. B may or may not be celebrity, we don't know. But we certainly know that A is not a celebrity, and then we remove A and push B onto the stack. If A does not know B, B may know A, or B may not know. If A does not know B, means B is not a celebrity, because by definition of celebrity should be known to everybody. And in this case, A does not know B, so B is not a celebrity. So we remove B and push A onto the stack. So look what has happened. We remove 2 people from the stack. We either put B or put A. We're putting only 1 person on the stack. So my stack size becomes n minus 1, and keep repeating it till I basically left with only 1 person on the stack. Let's say that person stack left is person number K. When only that person remain on the stack, we ask that person K, do you know all the other person 1, person 2, person K minus 1, person K plus 1 to person K. So once we have only one element on the stack, we are going to ask only n minus 1 question. And if the person say, I don't know anybody, the person is a celebrity. If he knows anybody, is not a celebrity. So what is my time complexity here? If you look at my time complexity, I'm removing 2 persons, so I'm doing 2 work, and I'm pushing 1 person back, so I'm doing 1 work, so that means 2 plus 1. So each time I'm doing 3 times work, and total, since I have n elements, I'm doing 3n work, and that is where the 3n comes in. So by push and pop requires 2 work, push requires 1 operation, total I'm doing 3 operations. Since there are n elements, I'm doing 3n work here, and when I finally get 1 person at the end, we do order n work there, and that basically means order n. So this is 3n plus 1n, it is still order n. So using decrease and conquer, using a stack, I can solve this problem using order n time, where my other approaches of using adjacency matrix, adjacency list, or even the decrease and conquer by 1, calling a function n minus 1, they all give order n square problem, but this one gives order n time. And that way you can approach the problem differently. So whole approach of algorithm is look at what by data structure that can use, how can reduce the problem size to smaller, and then solve it. And those who want to explore, I would say write a program using all the 4 approaches and see does it work you. And that's all I have for today. So to summarize, we looked at advantages of and disadvantages. Advantages, if we can solve a smaller problem other than solving brute force. A smaller problem could be solved in parallel. A smaller problem are easy to solve. Is the benefit. Disadvantage is because it heavily depends upon recursion. Recursion involves stacks. We need to build memory. Recursion requires clarity of thought. If you make a mistake in putting a right termination condition, it may not ever happen. It may not never terminate. Or if recursion size becomes too big, we run out of system memory, and those are the disadvantages of decrease and conquer. That's what you look at. And then we finally looked at a simple application celebrity approach, and this is what we did. So thank you, and in our next class, we start looking from beauty algorithm. Go ahead. And in case you have any questions, please feel free to ask, or if not, then we can go and resume back. If any questions, please let me know. Any questions, and we should be fine. If no question, then I'll probably. If any questions, feel free, and we should be fine. If not, I'll stop sharing my screen. Continue to raise questions, you can ask it, whatever, that should be fine. Otherwise, your time. Please stay safe, stay healthy, fight the virus together. What the PM said. Just follow it up. Spend your time reading. In case any questions, send me an email or you can call me at my number. And my number is 89700000559. You can call me at that number to ask any doubt, and that should be fine. Thank you very much. Again, I'll make the recording available and you can watch it, play it, and do that. If no questions, I'm terminating. Thank you.